unlight a fire that I spent the last 15 minutes lighting. So we do have a projector, and we'll go ahead and get started pretty much on time. So Dr. Field.
Hi, I'm Dr. Brandon Field. It's my great pleasure to introduce the team here that I had the joys of advising this semester. They did a project with Consolidated Grain and Barge. I'll let them tell you about it. But it was especially a pleasure to do this team because their liaison that they were working with was one of our former students that I advised his senior project several years before. So students keep graduating, but I'm not getting any older. So anyway, I'm going to hand it off. Rachel, Tim, Michael, and Jordan.
Let my advisor sit down. Hello, everyone. As he said, we designed a central vacuum system for Consolidated. This is the brief outline of our presentation. We're going to start with the background of the company, then we're going to talk about what the company really wanted from us. Then we're going to break that down into the subsystems, which are the piping, the backhouse, the electronics. Then we're going to talk about the bids, and then we're going to explain our design choice and why we chose it. Now, Consolidated Grain and Barge, or CGB, was established in St. Louis in the 70s. It's privately held by global companies, and basically it does anything you need it to do with grain. It does the business side of things with risk management and financing. It also does actual processing of grain, selling, shipping, all of your grain-based needs. The plant we specifically were working with is in Mount Vernon. It was built in the 90s, and it processes over 30 million bushels of beans annually. That is a lot of soybeans. Over 900 million, actually. And this is the process that the beans go through in the building. They come up here as whole beans, they get dried out and cleaned, heated, dried again. The hulls are removed here, and then the rest of the hulls, and then they're cracked, and then they're flaked. And at that point, they can be processed into meal and oil and all the other things that soybeans are used for. Now, you can see in some of these pictures that this is actually on a graded floor. And as you might imagine, this process creates a lot of dust. And dust can be a serious problem. Any particulate matter, if it's soybean dust or flour or rice or anything, if you get enough of it, there can be an explosion with the slightest spark. So OSHA has very strict requirements on how much dust can be built up around grinding equipment, about 1/8 of an inch. But nobody wants to dust that by hand because that would be terrible. So instead, they wanted a central vacuum system that would fulfill this need. It needs to be able to process whole soybeans as well as the dust, handle up to 800 pounds an hour. And one of the really important requirements that they had was it needs to be usable by 2 different people at the same time. So someone can be vacuuming on the bottom floor and someone can be vacuuming on the top floor at the same time. And obviously it needs to reach all 7 floors and reach all the corners. There were some requirements as to the back house, which is where everything would be processed, where the air would be cleaned out. They didn't want it on the north side of the building, and they needed it to discharge to a dumpster. And they wanted the entire system to have a single kill switch. And obviously everything needs to meet OSHA standards. This is the subsystem breakdown. There's the piping and everything involved in that, which will be handled by Jordan. dust collection, which will be handled by Tim, and then there's the electronics, which will be discussed by Michael. The entire system will end up looking a little bit like this. Things will be picked up by the vacuum port, processed in the baghouse, and then the clean air will be shot out through a fan. And the first and possibly the most important system is the piping, which will be handled by Jordan.
Okay, so yeah, I was the lead on the piping, and basically my responsibilities were to come up with a layout. Ended up coming up with 3 different layouts and then recommending one, looking at the fittings and the piping. So some requests from CGB, they wanted a layout with 3 hose connections per floor. They also wanted an additional design with 4 hose connections per floor. Basically what I'm referring to as a hose connection is where the flexible hosing is going to attach to the ductwork, to the hard piping. They wanted the equipment on the roof of the flaker building, which we'll see in a minute, and then a 40 feet flexible maximum tubing, flexible tubing. So some things that we focused on whenever we were designing the layouts. So we wanted to minimize the amount of hard piping fittings and flexible hosing, mainly from a cost standpoint, but also to lower the pressure drop of the system. We wanted to avoid any existing equipment, sharp turns and fittings. This shows the difference between a long radius 90 and a short radius. Obviously, we want to use the long radius 90s wherever possible. Lastly, allow for simple installation and easy and efficient operation. So an important design choice that is shown here in the figure is the way that the branches will tee off from the main trunk. You can see the vertical component here is what we're referring to as the trunk, and then the branches will be run underneath the flooring. Again, this is graded flooring. And then you can see here, these are actually what I'm referring to as the hose connection points. So with this design, a single branch will ultimately serve 2 floors. You'll be able to attach a flexible hose here and here, and for example, will service the 3rd and 4th floor. So this is layout 1. You can see there's a lot going on here. This is actually the 7-story preparation building that requires the central vac system. And then this building, this 2-story building here to the right is what we're referring to as the flaker building. This is all the equipment on the roof of that building. So this is like the dust collector, the vacuum source, and the motor. And this discharge line goes to a dumpster on ground level. But then the main body of this is the piping, the ductwork. This layout uses 1 single trunk and 3 hose connections per floor. Shown to the left is what a hose connection would actually look like in person. This is a flexible hosing attaching to the hard piping, and basically it's just a little flat floor deal. And then here at the places where the branches tee off in the main trunk, we're going to use something called a double lateral. So this is going to be like the trunk, and then here's your branches starting off with 45-degree elbows, compression cup. This is the same layout from a top floor plan view, and then showing the range of the 50-foot flexible hose. You can see it covers the entire floor. So this is layout 2 from a different view, from a side view, but a lot is the same. The equipment's on the same flake roof building, and basically the main difference is there's 2 trunks in this design and 2 hose connections per floor. Again, a top view of layout 2 with the trunks shown here. They will be along the north and south faces of the building, with the branches teeing towards the middle. And then again, the range of the flexible hosing, a lot more efficient use of the flexible hosing here. Lastly, layout 3 uses 4 hose connections per floor and a single trunk. So the single trunk's basically in the direct center of the building. This might require some moving of equipment, and then the flexible hosing has a lot of overlay here, so you're not going to miss any part of the building with this layout. To begin calculating the airflow and pressure loss of the entire system, again, we had to look at what CGB was requiring. They wanted a design that could handle 400 pounds per hour and an additional design to handle 800 pounds per hour. basically, I was able to find a lot of properties of soybeans from Cincinnati fan source, and using those properties, specifically the CFM per pound for soybeans, to find out how much CFMs, which is a measurement of airflow, we would need for 400, 600 pounds, and 800 pounds per hour. And using this ductulator shown here, to actually size what size pipe we would need that rate of airflow. A quick summary of the findings. Again, the nominal requirements, 400 and 800 pounds per hour. Basically, a 3-inch pipe can supply 433 pounds per hour and meet the lower end of the recommended range. And then 4-inch pipe can supply almost 750 pounds per hour. Highlighted in green is layout 2 because it has the lowest pressure drop, and from this point on was our recommended piping layout. Now I want to hand it over to Tim to talk about the dust collection system.
Good morning, everyone. I was the lead designer on the dust collector part of the system, and the dust collector, what it does is it removes debris from the airstream or filters it out. There's 2 main kinds of dust collectors used for this application. On the left here, you have a cyclonic dust collector. It uses centrifugal force to remove particles from the airstream. It typically is used as a pre-separator or for larger particles. On the right is a baghouse dust collector, and it uses filter media to remove debris from the airstream. The baghouses are highly efficient and can remove much smaller particles. Soybean dust it averages about 1.5 to 40 microns. So we've selected the baghouse dust collector to serve for this system. Now, in choosing a baghouse, we have several design choices that we had to make. First was whether we're going to use a positive or negative pressure system. A positive pressure system basically pushes the air through the baghouse, and that means the dirty airstream must travel through the blower before it reaches the baghouse. The negative pressure system, it pulls the air through the baghouse, so only clean air goes through the blower. So because of the abrasive nature of soybean dust, we've selected the negative pressure system. Now, manufacturers, they categorize their baghouses due to the cleaning method that they have. Besides just a manual cleaning style, the mechanical cleaning is a mechanical shaker, reverse air, and a pulse jet. Now, I sent out requests for about 8 quotes from different companies, and we only got 2 back. And one of them was a manual cleaning system, and the other was a pulse jet cleaning system. And the filter material, I'll cover that in the next slide. Our design calculations, the most important was the pressure drop of the baghouse system. And basically, to calculate that, you take the resistance of a clean filter plus the resistance of a dirty filter, and that will give you your pressure drop. For the can velocity, which the can velocity is how fast the airstream is moving through the baghouse. And you need the air to slow down through the baghouse so that larger particles will fall out. And typically for the soybean dust, you want 300 feet per minute or less value of that. And we use that can velocity with the air to cloth ratio, and that helps us calculate how much area of filter and how big the baghouse needs to be. Here's a picture of our filter media and different types of filter medium they use for different applications. Now, the Consolidated Grain and Barge, main applications that are needed is abrasion resistance and cost efficiency. And highlighted here, the polyester filter media has excellent abrasion resistance and it's very economical. So just to recap the design choices and calculations, we want a bag house to do the dust collection with a negative pressure system, polyester fiber, and the system that we chose out of what our bids was a pulse jet cleaning system. Our design calculations were at least less than 6 inches of water column pressure drop, a can velocity of 300 feet per minute or less, and an air cloth ratio of 7-to-1 or 8-to-1. Now I hand it off to Michael for the electronics.
Okay, the electronics of the system need a blower, a motor, and a controller. The blower needs to be sized first according to the needs of the system, namely the volumetric flow rate and the pressure drop. The motor needs to be sized according to the blower, and then the controls need to be compatible. Initially, it was expected to use a centrifugal fan as the vacuum source. However, due to the relatively high pressure drop, 4 to 6 inches of a column of mercury, a positive displacement blower is the type that needs to be used. The image is of a positive displacement blower. The table compares a couple of different positive displacement blowers and their pressure drops and volumetric flow at a certain speed. The BHP, or brake horsepower, is the horsepower actually required by the blower to run the blower at that particular speed for those situations. Some of the considerations for the different components were the interface. The gears or a belt and pulley to couple the motor and the blower together need to fit together seamlessly. There need to be safety shields in place. And as we mentioned before, the blower and the motor were placed on the roof of the adjacent flaker building. So it needs to have some sort of stand to fit on. All of these need to fit together seamlessly. All of the holes need to line up properly. Therefore, it is recommended to have all of these from a single source. We actually received 2 different quotes or bids, and with just a cursory glance, you'll notice that the quote from Vector is about $10,000 cheaper than the quote from Kais. However, the system is not as robust. It doesn't have the volumetric flow capacity or the pressure drop. Also, the system from Kais has a better quality of attachments, such as a explosion venting in the bag house or a static dissipating hose. So we actually chose as our design recommendation the system from Kais, and here are some specifications of that system. 16 gauge straight piping, all the fittings and elbows that we need. The bag house is fully contained, 75 square feet of filter, explosion venting. Also, it has a pulse jet cleaning system that Tim mentioned. It is a single system for electronics, a positive displacement blower, and a 25 horsepower motor. This positive displacement blower and a 25 horsepower motor from NEMO. Also, Kais does automation control. Some of the accessories included with this system are a static dissipating hose and hose attachments. So our design recommendation is the Kais system quote, which has a capacity of about 600 pounds per hour. It has a better capacity, or better protection against dust explosion, has better quality attachments, and Kais can modify the controls. We recommend layout 2 because it is the lowest cost in terms of pipe and fittings. Also, it has the lowest system pressure loss. This can equate to long-term savings because the lower pressure loss requirements requires less horsepower by the motor. It is expected to have easier installation and better maintainability and ease of operation. This entire system costs about $40,000. We would like to thank our liaison at Consolidated Grain and Barge, Mr. Lewis Bowles, for giving us the opportunity to work on this project. Our advisor, Dr. Field, for advising and encouraging us throughout this project. The engineering department chair, Dr. Mitchell, for overseeing our engineering education. the engineering faculty for teaching us along the way, and Mrs. Donna Moore for being the glue that holds the engineering department together.
All right, they're not quite done though. All right, questions?
Can you explain how the pulse jet cleaning system works and how much manual interaction there is in getting the junk out of the filters and into the dumpster?
Well, the pulse jet uses high pressure air, and it will push that through the filter media when the system's not running, and that'll dislodge it from the filter. And we have a rotary lock on the bottom of the hopper which will turn and exhaust the debris. Now, for the manual system, you would actually need to pull the filter out and take it to a dumpster or waste container and then basically shake it out or blow it out with the air compressor.
So are there any negative consequences to having your blower and motor up there on that roof of that building?
Well, it would be more exposed to the elements, but it's a contained unit and they're actually designed for being outside.
Other questions?
I have a central vacuum system at home, so I was very interested in this. And once ours got stopped up. So my question may be for Jordan. Suppose there's a stop up before the bag system, back in the pipe area. How do you clean it out?
That's a good question. Kai's actually included something in their quote called a stock chamber. Basically, that's going to go, if we go back maybe to the drawings.
Which one?
Any of the layouts will work. Basically, it's a large area, and basically it would attach here, and you would be able to clean out any large debris that might fall on that location.
I have a little bit of experience with soybeans because we live on a grain farm, and if soybeans get wet by chance, they swell up. And so would that be a problem in the pipe system?
Yeah, I think that would cause problems, but these soybeans are coming straight from a storage bin on site, and then enter the inside of a building. So I think it would be a little hard for the soybeans to actually get wet in this system.
Other questions? Okay, can you go to your 3 vacuum layout, the overhead view? Okay.
This
not-
one, sir?
Yeah, not to quibble, but you've got a corner there by the stairwell that's not covered. And you did integrate the three hose system into at least a couple of your floors. What's the deal with that? Did you not notice that, or is the owner okay with that, or do you have another plan?
Are you referring to this little section right here?
Yep.
I'm not gonna lie, I honestly did not notice that. We weren't responsible for cleaning the stairwell, which is why you kind of see the dog leg left of the
Okay.
piping. But, that might require just a little bit more than the 50-foot hose right there. So maybe a recommendation would be to maybe not have it dog left to the left as much.
Okay, yeah, because you've got a lot of excess coverage off to the one side,
Yeah.
and you don't quite have that one corner covered.
Also, it's worth noting that on the layout that we actually do recommend, there we're actually recommending, and this one has complete coverage.
Well,
Well, except for those
it
corners.
is. Yeah, except for some of the corners. All right, any other questions?
How long do you think the system will last?
I don't see this needing replaced anytime soon. It's carbon steel piping. The blower is quality from Kai's Industries. If I had to put a number on it, 8 to 12 years.
All right, any other questions? All right, let's give them a hand.